Let's start chapter 6.4, which is about trigonometric substitution. I think another name for it could be reverse substitution, because we'll be doing the opposite of what we did with U substitution. You might ask, why should we care about this stuff? Well, it's really handy for formulas involving circles, and some physics formulas involve distances like square root of x squared plus b squared, and this technique is just what we need to solve things like that. As you might guess, we're going to be using a lot of trigonometry, trig identities, so here's a bunch of reminders. You might have seen the phrase SOHCAHTOA before. Try to remember what that means if you have heard it before. It means sine is what? Opposite, that's the O and so, over adjacent. And then cosine is adjacent, sorry, boy, I messed that up, huh? Opposite over hypotenuse. Cosine is adjacent over hypotenuse. And then tangent is opposite over adjacent. So we'll be using those in various combinations. Sometimes we use x for trig or t. Here it's common to use theta, the Greek letter theta, which is like an O with a horizontal line drawn through the middle, not a zero. A zero would have a diagonal slash through it. And some of our favorite trig identities are sine squared plus cosine squared equals 1, which we often reformat to say if you have something like 1 minus sine squared, that's cosine squared, or if you have 1 minus cosine squared, that's sine squared. We also sometimes use tangent squared plus 1 equals secant squared. I always have a hard time remembering that, but if you start with sine squared plus cosine squared equals 1 and divide everything by cosine squared, sine over cosine is tangent, so sine squared over cosine squared is tangent squared. So cosine squared over cosine squared is 1, and then 1 over cosine is also called secant, and then we're squaring that. And then you could solve that and rewrite it that way if you need to. We'll also be using this double angle formula, and then these squaring formulas a lot. All right. So before we get into reverse substitution or trig substitution, let's go back and think about U substitution so we can draw parallels and contrasts between them. If you had this problem, I'm going to suggest you do U substitution, so practice it yourself right now, pause the video and come back. All right, so you would probably say U equals the stuff inside there, 1 minus x squared, and then du equals negative 2x dx, and then solve both sides, solve by dividing by negative 2 on both sides, so you'd get 1 over negative 2 du equals x dx. And then you'd rewrite the integral. Oh, and look at that, we've got an x dx here in the integral, pretty handy. So we could rewrite the integral as the integral of 1 over root u times 1 over negative 2 du. Might help to rewrite that as a power. That's u to the negative half times 1 over negative 2 du. And then do the power rule on that, and we'd get u to the positive 1/2, 1 over positive 1/2, times 1 over negative 2, not du, just plus c. And then substitute back, right? So 1 over 2, u becomes 1 minus x squared to the 1/2 times 1 over negative 2. And you could simplify it from there, but that's not really the point here. Let's point out our new variable u is a function of the original variable x. So what do you think will happen with reverse substitution? Another thing to point out is that we needed just the right thing in the integrand, this x, to combine with the dx so we could substitute it out and replace it with something involving du, which we're not going to need here in reverse substitution. So in reverse substitution, we're going to be able to just substitute. It won't be exactly dx for du, but it'll be at least easier. We won't depend on having exactly the right thing. So let's do a problem that's similar to this. It's a problem that doesn't have any great applications, but at least it gives a fairly straightforward bunch of math steps, and then we'll do one later that has better applications. So let's say we did the integral of 1 over root 1 minus x squared dx. So can you see the parallel between what we're doing here and what we're doing up here? Here we had the x, here we just have a 1. U substitution would not work. So what can we do? Well, maybe reverse substitution, but what does that mean? If this subtraction wasn't here, I could take a square root more easily, right? Can we think of anything in the world where if I had 1 minus something squared, I could turn that into something else squared and then take the square root? So if that was 1 minus sine squared, I could replace it with cosine squared. And then I could take the square root of that and everything would be easy. So if that x was a sine, then life would be easy. So let's try saying x equals sine theta. Saying if I had a sine squared there, it would be a lot nicer. If that's true, then what is dx? Well, we do this part the same way we do u substitution du. Just take the derivative of the previous thing. So it would be that prime times d theta, which would be what? Cosine theta d theta. So this says anywhere you see a dx, you can replace it with cosine theta d theta. So now let's rewrite the integral in terms of our new situation, new variable. So we'd have 1 over root 1 minus sine squared theta times, and then the dx becomes cosine theta d theta. I don't have to worry about combining stuff. So that's nice. And then we'll use a trig identity here. So let's highlight the dx became cosine theta d theta. 1 minus sine squared equals cosine squared. And what can we do then? We get integral of 1 over root cosine squared theta, cosine theta d theta. Let's simplify this a little bit before we try taking antiderivatives. What's root cosine squared? That would be 1 over cosine squared. Just 1 over cosine times cosine theta d theta. And what happens when you multiply 1 over cosine by cosine? You get 1. And what's the integral of 1? Well, if it was the integral of 1 dx, we would say the integral is x. Here, if it was 1 dt, we would say the integral is t. So now the integral is just theta. And now we'll back substitute. That's a little trickier here, but not terrible, because before, when we had like u equals 1 minus x squared, then when we back substitute, we can just plop in something. But now we don't have an expression for theta. What we have is x equals sine theta. So let's think about that. If x equals sine theta, what can we say about what is theta all by itself? Well, you could take the inverse function of sine, which is also called arcsine. So you could say arcsine x equals theta. Oh, let's draw a real theta. Theta, like that. So anywhere you see a theta, you can replace it with arcsine of x. Arcsine is also written as sine with a -1 power, but it's not really a power. It's not really an exponent. It's a notation that means inverse function, but it doesn't mean 1 over sine. So let's say it's not equal to 1 over sine x. So it's possibly the world's worst math notation. Anyway, now that we know that theta equals arc sine of x, we can just replace theta here and say arc sine of x plus c, and we're done, right? We might want to check it. Maybe we should go graph it in Desmos. All right, here we are. We've got our original integrand, 1 over 1 minus x squared. We didn't really stop to think about where that's defined, but apparently it's defined only between -1 and 1, because if x is bigger than 1, then 1 minus x squared is negative, and then we would be trying to take square roots of negative numbers, which if you want to stick to real numbers, you can't do. Then we've got the antiderivative we just figured out, arc sine of x, and if we plot the derivative of the antiderivative, that seems to line up nicely. So we've done this using a substitution of x equals sine theta. In the homework, you're going to do x equals cosine theta on the same problem, and we'll see if you get the same antiderivative or if you get a different looking antiderivative, and whether you can justify that you could get one thing or the other and somehow they're both right. So that'll be the first big homework problem.